Okay, this is just a very quick addendum to the previous video, at the end of which I covered problem 1964, and I tried to calculate the work done on the gas using an alternative method, and it didn't work out. Well, I'm sorry to have wasted your time. It was just a trivial error with the calculus there. Rookie mistake. I'll show you what I mean. The integral of x to the a dx, as long as that integer is not -1, if it was -1, you'd have to use the natural log function. But for any other value, it's x to the a plus 1. You raise the power, but then divide by that new power. And I simply forgot to divide by that new power. So I'll refresh your memory. We were looking at an adiabatic compression, and we know that for an adiabatic process, P times V to the gamma, that never changes. The pressure might be going up or down, the volume might be going up or down, but this product is always equal to a fixed value. So I evaluated this at the initial conditions, which was STP and some volume like 11.2 liters. I found that this was the value of the constant. And then I decided, instead of using the first law of thermodynamics and equating the work to the energy, which I calculated using the constant volume heat capacity, instead I just decided to do the work integral directly. Because now that I know what this constant is, I can solve for P. It would be 188.114 times V to the negative gamma. Solve this for P, plug it in here. And this is an easy integral. We just have to use the power rule. So I was correct to raise this power to negative gamma plus 1. And since this exponent is not -1, it is valid to use the power rule. I just forgot to do this. I forgot to divide by the new power. So 1 minus 1.4, we've actually got a -0.4, so the minus signs cancel, and that takes care of my first issue, which was that I wasn't expecting the minus sign because I know that for a compression, the work done on the gas is positive. And sure enough, when you divide by 0.4, you get to within 3 sig figs, or 2 sig figs, the same answer that I got using the method presented in your solutions manual. So by using the first law, we found that this was the work done on the gas. 38.48. Here I'm getting 38.38. That's just rounding error.